Good morning, ladies and gentlemen. My name is Jan Suwczyński, and as a co-organizer of today's colloquium, I welcome all of you. Today we are going to host Professor Jeroen van den Brink. He originates from Netherlands and he worked there for some years. Now he's in Dresden. He's a professor and director of the Institute of Theoretical Solid-State Physics in Leibniz Institute for Solid-State Physics and Materials Research in Dresden. His scientific interests concentrate but are not limited to strongly correlated electron systems and physics of magnets. He has published around 300 scientific papers, and 1/3 of this has been published in physical review letters or in journals belonging to Nature Publishing Group. Today you are going to hear about altermagnetism. Altermagnets is a class of materials that share properties of antiferromagnets and ferromagnets, which make this class very unique. Possibly it is a new type of magnetism. And I hope that today we are going to learn more about this. So, Jeroen, the floor is yours. Welcome to our faculty. Go ahead.
Okay, now you should hear me. Okay. Thank you for the very kind introduction. As announced, I'll talk about altermagnetism, which is a topic that is relatively new. I would say it's in the baby years, and there's a lot of activity going on. I decided, and also was asked, to give a general introduction. So I'll even introduce to you what ferromagnets and antiferromagnets are in order to get to altermagnets and give you an idea of what is the excitement about, rather than go into all the detailed things that we are doing now, not only in Dresden, of course, but in many other groups. The work I'll present today is done by our institute in Dresden, the Leibniz Institute for Solid State and Materials Research, and I'm also at the university, collaborations with Würzburg, with Stuttgart, and I should also mention colleagues at KTH in Stockholm, in Sweden, where our latest work that I'll show you a little bit originates. Okay, so as I told you, we are being very active. These are the recent last year's preprints that came out just from us. On which materials are altermagnetic, what kind of new effects you can expect, anomalous Hall effect, and how to understand it. Piezomagnetism driven by fluctuations. What do spin textures look like, and what are their properties in altermagnets? And last Friday we put out a preprint showing that their altermagnets can be topological. They can have while nodes. Okay. Instead of going into all this detail, let me just start from the beginning talking about magnetism. So let's suppose we have a lattice. And we consider a two-dimensional lattice of, let's say, atomic sites that are at the vertices, that are labeled with I. Can you put it a little bit less loud? I hear myself. So on each of these vertex, I can imagine that I have an atom that carries a spin, and the spin can be is denoted by this vector S and an arrow. And I assume there's interaction between neighboring spins on this lattice. So here's this idea. I have I and J labeling these lattice sites. I have two spins sitting there. And there's an interaction between the spins, which is just their dot products, right? Now, how do I get ferromagnetism? Well, if the interaction here, this J, is smaller than 0, the spins want to be parallel, and I get a nice lattice of parallelly oriented spins, and I get a ferromagnet. So what can I say about the symmetries there? Well, the symmetry is actually very simple. You can see that the wave function actually, if this is a quantum system, the wave function should be invariant for translation by one lattice spacing. It's obvious. And the consequence of that is that the spin or the magnetization on each lattice side is repeated, so I get a finite total magnetization. The way this kind of material, or well, this kind of ferromagnet is often described is by a Heisenberg Hamiltonian, which just says I sum over all neighboring, in this case, neighboring lattice sides, the Si dot Sj interaction, and have an interaction that is independent on which bond I'm considering. I get a Heisenberg ferromagnet. Okay, so now these are localized spins that you can imagine sitting on a lattice. The other thing you can imagine is itinerant electrons that are living on the lattice side, and they can also be spin polarized. So now if I have electrons hopping around in a lattice, you will have bands, you will have dispersions of those electrons. And instead of thinking about localized spins, I have to think about the properties of the bands of the electrons. So now I think about a band ferromagnet, where now I have one band. This is momentum, this is energy, and this is the Fermi level. So below the Fermi level, the bands are filled. And this blue band now is a band for the spin up electrons, say, and the red band is for the spin down electrons. And you see that the Fermi levels, well, the Fermi level is one energy, of course, but it cuts the bands at different momenta, meaning that this band is less filled than the band below, and that the system has a net ferromagnetic polarization. And why are these bands split? Well, these bands are split because there are electrons sitting on the lattice side, hopping around, and if there's another electron coming there, then this is at a different energy, it is repelled. So there's an exchange splitting, a local exchange energy on this atom that puts one band higher than the other band. The symmetry is very similar. So actually, this is what happens in your ferromagnetic iron, your ferromagnetic nickel, your magnet that you put on your fridge. Yeah, so the bands are what they call spin split. The magnetization of one band is different from the magnetization of the other band. But again, the wave function is invariant for translation by one lattice spacing, and I get, because of the symmetry, a total finite magnetization. Okay, now what is an antiferromagnet? Same thing, only the interaction here changed. Instead of having parallel spins between lattice sides, I can have anti-parallel interaction that favors anti-parallel spin. So if this J larger than 0, Si tends to be opposite direction than Sj. And here now I have a two-dimensional antiferromagnet described by, again, the Heisenberg Hamiltonian. So what are the symmetries here? Actually, the wave function is invariant for translation by one lattice spacing, but I have to also do time reversal. If I go from one lattice to the other, I have to flip the spin, in simple words. Yeah. This happens in, for instance, lanthanum copper 4, the starting compound for the high TC superconductors. But of course, there are many, many more systems like that. So what are the consequences of this symmetry that I have here? Well, obviously, there's zero total magnetization because the two lattice sides, the two sublattices, they completely compensate. And there's a other consequence, which is maybe intuitive, but to prove it, I would need 10 minutes or so, or 5 minutes, but which I don't have. So you have to trust me that there's a degeneracy at each momentum, the Kramer's degeneracy at each momentum. Yeah? So instead of having like in a ferromagnet, I have a minority spin and a majority spin bands that are split. Now, in this case, for this type of antiferromagnet with this symmetry, situation is like this. Again, I have energy and momentum, so a dispersion relation. I have maybe 2 bands, but each of those bands is twofold degenerate. So the up and the spin projections for each band are the same. And I indicated that by this blue band with red dotted line and this red band with blue dotted line, but it's immaterial. These bands are twofold degenerate, at least in the case where there is no spin-orbit coupling. So there's no spin splitting, and a situation, I just took one here, this is barium-2 iron arsenic, which is also a well-studied compound for, it's, again, the starting compound for a class of superconductors. But also in this band picture, I have this, in this band picture, I have spin degenerate bands, which obviously also means that I have 0 total magnetization. Actually, at each momentum and each band, I have 0 magnetization due to this Kramer's degeneracy. Okay, so now these were the ferromagnets. Could you really put it a bit down, the sound? I mean, I hear myself, or I should speak less loudly. Maybe that's better, yeah? Yeah, for me, yes. We had the ferromagnets, we had the antiferromagnets, now I'll get to the altermagnets. So, and I'll give you the simplest example of this is the, what I'll call the checkerboard antiferromagnet. So now suppose I have a system that has both antiferromagnetic interactions, like before on the square lattice, which are the brown lines here, and there are diagonal interactions which are ferro. So if I'm sitting on this, well, let me take this side here, I have 4 neighbors that are antiferromagnetically coupled to the spin here in the center, and 1, 2 neighbors on the diagonal that are ferromagnetically coupled to it. Okay, and you can ask the simple question, what will be the magnetic ground state of this? And the answer is not so difficult. It's the same antiferromagnet that we had before. Look at these spins. Here was my side. This one has spin down. It has 4 neighbors that are spin up, so antiferromagnetically coupled to it, that's fine. And here, 1, 2 neighbors that are ferromagnetically coupled to it. That's for this red downspin, and for the blue upspin situation, it's the same. The 4 neighbors here are antiparallel to it, but now on this other diagonal, so rotated 90 degrees from this diagonal, but on this diagonal, the coupling is ferromagnetic. So also there, the spin bonds are satisfied. So there's what we say unfrustrated antiferromagnetic order. And you can ask, is the total magnetization 0 by symmetry? And it is. It clearly is for this ground state. Yeah. And what is the symmetry? Well, it's not, is it like for the antiferromagnet, a translation by 1 lattice spacing and time reversal? Well, if I would take the spin here on this side and translate it by 1 lattice spacing, I have to think about the interactions here. These interactions for this up spin, or for this up sublattice, are along this diagonal, the diagonal going to the right upper corner. Now, if I translate, I get to the down sublattice, the spin reversed sublattice, but the interactions are now along the diagonal going to the left upper corner. Yeah? So you can already see the Hamiltonian is different. The interactions are different for the two sides. Yeah? So it's not the symmetry lattice spacing times time reversal that will not leave my ground state wave function invariant. It's something else. And actually, it's because the diagonal interactions on the two sublattices of this antiferromagnet, of this checkerboard antiferromagnet, are rotated by 90 degrees. So what I will have to do to my wave function is translation, time reversal, and this rotation. This 90-degree rotation. And you can show that for this antiferromagnet, that will leave it invariant. Yeah? So now let's go to why this is an altermagnet, or what are the kind of the definition of the altermagnet. I will not go very formally on you, just loose and easy, and believe me, you can formalize everything until, on the level of group theory, so it's all there. But let's say I have a material that has collinear magnetic order, so spins are parallel or antiparallel. All spins are parallel or antiparallel. Its magnetization vanishes by symmetry. And this symmetry is not just translation times time reversal. And in general, well, this is a bit a sloppy statement, but for pedagogical purposes, the magnetic ordering does not enlarge the unit cell. So you see, if I have these two spins sitting here, to describe this system, I need to take these two sublattices into account separately. It's not just a translation, it's this translation, or this system has the interactions like this, and the next side has the interactions like that, making these two sides inequivalent. So if I build a unit cell, I need to take these two sides into account from the beginning. Yeah? So now let's go, this was the localized limit, the localized situation for an altermagnet involving this rotation. What does it mean if I go to the band picture? If I go to the band picture, I have the following situation. This is a band altermagnet. So the bands are spin split in general, because the wave function, to get from one to the other band, I would also need to do a rotation. And if I do a rotation in k space, I rotate kx into ky, for instance. I rotate the momenta. Yeah, so if I have the wave function at one momentum, I do these symmetries, I do this rotation, I get to a wave function at another momentum. Yeah. So these are not, there is no invariant to it. I just map one momentum to the other momentum. So there's no reason to have a spin degeneracy, there's no reason to have a Kramers degeneracy of these bands. So what the band structure looks like, that is, let's say, for one spin species, there's spin splitting, and the up spins are lower than the down spins at some momentum. And at the other momentum, rotated by 90 degrees, pi over 2, again, I have the spin splitting, but now the down band is below the up band. So in total, if I count the number of up electrons and the number of down electrons, it's the same. This is a spin compensated, a total magnetic moment zero system. And that's true for wherever the Fermi level is, right? It's this 90-degree rotation that takes care of the total magnetization vanishing in this system. So there is a spin splitting of bands possible, or at a generic momentum, but you see here, I took momentum 0, I didn't write it 0, but let's say this is 0, and there the bands are degenerate. And you can also show that generally the spin splitting at high symmetry points or lines or planes in the Brillouin zone vanishes. So there's no spin splitting if you only look at these high symmetry points, because these high symmetry points can have rotational symmetry, actually. Yeah? So, and probably this is the reason why people doing band structure calculations were not really aware of this possibility to have antiferromagnets that have total magnetization 0 and still split bands without spin-orbit coupling. Because you have to look at the generic point in the Brillouin zone, which if you do a band structure calculation, you don't do. You stick normally to high symmetry lines and planes. I'll say a bit more about the history of altermagnets later. So this is my fast and loose approach to altermagnets. Collinear magnetic order, magnetization vanishes by symmetry. Magnetic order does not enlarge the crystallographic unit cell. So the vanishing of the symmetry is guaranteed by symmetry other than translation, or more than just translation. Yeah? The eigenmodes of the system, the bands, but I will show you also the magnons in a localized altermagnet, the eigenmodes are generally spin split. And the reason is that momentum is not invariant for rotation, obviously. So in the itinerant spin materials, this means that the spin splitting does not require spin-orbit coupling, and it also means that the splitting, the size of the splitting, is given by the local exchange field. And if you're condensed matter physics, you know that spin-orbit coupling and local exchange are both there in general in materials, but the size of the spin-orbit coupling is generally much smaller than the local exchange field, except if you go to 4F but let's say for d electron systems, the spin-orbit coupling, so the magnets I talked about today and I showed you the examples of, chromium, iron containing and all that, the local exchange field is in the order of, let's say, 1 electron volt, and the spin-orbit coupling is in the order, or 1 or 2 order of magnitudes smaller. So we are having the spin split effect in the band structure, and there's a huge energy scale related to it, which makes it, gives this altermagnetism, let's say, it gives it a lot of horsepower. Yeah? So now the question is how you get this horsepower on the street, how you translate it into properties, but there's something big there that you have direct access to. So what I told you was none of it was invented by me. Yeah? I contributed nothing to this other than explaining it to you. I think people doing band structure calculations knew about the possibility, but never really made a point out of it, that you can have altermagnet, what's now called altermagnets, the spin splitting of bands. It went, let's say, unnoticed or unremarked until, I would say, the group of Alex Zunger, who pointed out in 2020, there's this giant momentum-dependent spin splitting in centrosymmetric antiferromagnets, now called altermagnets. There is then the group of Thomas Jungwirth, Jairo Sinova, Libor Schmeichel, who really put it on a different level because they understand the group theory structure behind all this. Yeah? That's very important, to put things on a formal basis, on a symmetry basis. And also this group then coined, after this paper, or maybe in this paper, this word altermagnets. Okay. So from their paper, I'll now take a few slides to again explain this altermagnet and give you one property that might be interesting, that might be, which definitely makes an altermagnet different from a ferro or an antiferromagnet. So here again, a ferromagnet with all these spins up. And now if I look at the Fermi surface, there will be two Fermi surfaces, because these bands that I showed you before cut the Fermi energy at a different momentum. So I have a large Fermi surface and a small Fermi surface for a ferromagnet, and this gives me a finite magnetization. Okay, what does the Fermi surface look like for an antiferromagnet? Well, the bands are spin degenerate, so there's no spin structure at the Fermi surface. Also, at the Fermi surface, all bands, all states are twofold degenerate. Now, this altermagnet. As I told you, this altermagnet involves a rotation if you go from one sublattice to the other sublattice, which means that also the Fermi surface is rotated if I go from one sublattice to the other sublattice, if I go from one spin to the other spin. So say for the upspin, I have a Fermi surface that is this ellipse elongated along kx. In that case, for the other symmetry-related, in this case spin down, Fermi surface, it will be an ellipse elongated along ky. And without spin-orbit coupling, without coupling these two guys to each other, or via orbitals to each other, this is the structure of the Fermi surface. And now let's look what happens if I would send a current. So you can imagine now, if I send a current along the x direction, these electrons moving will be different, or will have different spins, or different properties if they come from the two Fermi surfaces. Let's say electrons moving along kx will, let's say, mainly come from this blue Fermi surface, and less so from the red one. Yeah? And the same, so you can show actually that if you have a current going in one direction, in general it carries a spin, because it picks up the two Fermi surfaces in a different way if you project it along this direction. And now if you rotate, however, 90 degrees, you will have the same effect, but with the opposite spin. So depending on how you send your current in your altermagnet, it will be spin polarized up or spin polarized down. It's, it's cute, I would say. What might be practically relevant, who knows, is that you can make these spin polarized currents in an antiferromagnet. And this antiferromagnet has zero total polarization. So you can, of course, you have spin polarized currents in a ferromagnet, but the ferromagnet also has stray fields. It has this magnetisation that basically extends outside your solid as well. So you always have to take into account this long-range effects in the ferromagnet. In this case, in an altermagnet, the magnetisation is completely compensated. You don't have to think about or worry about stray fields, or very little about stray fields. And still you can have these spin polarized currents that you can basically choose the direction of by changing the direction of the current in the lattice. Okay, these are words, this is concepts, it's ideas. To show that this is the case, that you really can do something practically, is an entirely different matter, of course. Now, the step from concept to practical work goes via materials. And there are two materials that I will show you that are altermagnet. Oops, no, I did something wrong. There are two materials. So ruthenium dioxide is kind of the fruit fly of altermagnetism, and the other one is, thank you, chromium antimonide. So maybe say one word about ruthenium dioxide. It is the fruit fly, but it is a very unfortunate choice. It turns out that the magnetism in ruthenium dioxide is, well, it is heavily debated if it's there or not. It might depend on details of the material, if there are defects there. It is very unfortunate that this one is became the poster boy, girl for altermagnets. So the material here, there are materials issues. Chromium antimonide does not have any of those problems associated to it. So now this is our work, but I mean there's work before that showing the band structure, and I'm just showing you these are two different directions. So gamma x and gamma y are these directions along the x direction and the y direction that I showed you before. The blue and the red bands correspond to spin up and spin down. And you see that, indeed there is this splitting of the bands, but there is a magnetization, and the splitting of the bands is opposite if I make a rotation of pi over 2. Chromium antimonide is different. It has a hexagonal structure, so it is made out of triangles. So there are chromium triangle planes of chromium triangles and planes of antimony triangles that are interlaced or that are stacked on top of each other, if you wanted to see it that way. And the chromium planes are ferromagnetic, but if you go from one plane to the other plane, it's antiferromagnetic. So the total magnetization is 0. And you can show that actually if you go from one plane to the other plane, so if you want to relate the magnetization of the chromium here to the chromium in the next plane, you have to make a rotation of 60 degrees of the wave function, which is related to the way these triangles are stacked on top of each other. I think manganese telluride has a similar structure. So if you look at the band structure here, again, spin polarized bands all over the place. And now let's go to the question, can you see that experimentally? So this is the work done with my colleagues at KTH in Stockholm. We put it on the archive on Friday because on Wednesday, 3 Chinese groups put their measurements on archive. So I'll show you ours. So photoemission, what you measure in photoemission is the band structure, if you want, of a system. And what you're supposed to see here is, so this again is always momentum versus energy. And these are raw data. And if you have good eyes, you can see their dispersing bands. And if you look here, for instance, you see this is for different kz, so for different out-of-plane momentum, which you control by the energy of your electrons in photoemission. Doesn't matter, but you see here that there are clearly 2 bands. And if you look at the band structure, our band structure calculation, you'll see that indeed there are 2 bands that have this spin splitting. I just give you one example where the experimentalists also give the second derivative of their spectra. So here you see these 2 bands, this band here and there a band, and this guy and that guy. And the second derivative, you see that these are split by, in this case, 0.8 electron volt. They're also spin polarized to some extent. So this band structure that we calculated it's really there in the material. So chromium timonide, ruthenium dioxide, 2 examples. Are there more materials that are also altermagnetic? And we did a high throughput calculation, or better to say, that's Jorge Facio, who was a postdoc at our institute. He actually initiated this work. So you can go to a database, MagData, and look at all the materials. There are about 2,000 materials there that have the symmetries that might make them altermagnetic. And here is what we did. We found some of them are not altermagnetic, some of them in the calculations are not antiferromagnetic, some of them are non-collinear, and some of them we did this band structure calculations were too complicated, or we did not get a convergent calculation on them. And we are left with, or we showed positively, that for about 60 known collinear antiferromagnets, there are spin split bands and they are altermagnets, and they are altermagnets. Okay, so these, I just give you a taste. So here are materials, chromium, a lot of chromium, titanium, iron compounds, also here iron compounds. And what's on these lines are measures or that quantify the spin splitting. So you can see that the spin splitting for this material here is by all kind of different measures is large. Also here we have one that is large. So these are just measures that we defined for the spin splitting. And you can ask which materials have the largest spin splittings if you find 60 of them. And the chemical trend is that if you have strongly ionic materials, they tend to have the largest spin splittings. This is in itself not much of a surprise. What was kind of a surprise, or we would have liked it to differently, is that we found only 3 materials out of the 60 that are metallic. If you want to look at electrons carrying a current, an electrical current, but also magnetization, you need systems that are metallic. There are some systems that can be doped. So semiconductors, manganese telluride again comes to mind, that can be doped and therefore made metallic, but that are intrinsically semiconducting. We have some cases that we found very interesting. This is iron sulfide family, which tends to have very flat bands. And if you have flat bands, you know there are certain kind of instabilities. So the experimentalists at our institute are looking more deeply into this type of material. Okay, point. So there are a bunch of materials, about 60, 50, more than 50 of them are insulating. And if they're insulating, we can think about, again, this checkerboard lattice that I told about before. So if I take such a checkerboard lattice, such an antiferromagnet, are there interesting properties? So what we did is a calculation for a 2D square lattice. We wanted to look at properties, again, that are special for altermagnets. You take a Heisenberg system, Heisenberg coupling, also diagonal ferromagnetic Heisenberg coupling. Along one diagonal, you make it Jx, and along the other diagonal, Jy. So here we have this, along this diagonal, we have Jx, and on the other diagonal, we have Jy. And if Jx equal to Jy, you have the symmetry of rotation by 90 degrees if you go from one sublattice to the other sublattice, and you have an altermagnet. Okay. Now, how does this reflect this altermagnetism in this localized magnet, where I shouldn't think about electronic bands, but instead my excitations are magnetic ones, they are magnons. So, but I can think about magnon bands, and I have magnon dispersions. And you see here, these are the calculated magnon bands, and these are also, we have two, so this is momentum, the two-dimensional momentum, and on the this axis here, the vertical axis, we have energy. And you see there are 2 sheets, and these sheets are rotated by 90 degrees. So there are 2 magnon branches, and the magnon branches are rotated by 90 degrees. You can see it here. If you had a fixed energy, there is one magnon branch here, and the other one that's rotated by 90 degrees there. And actually, you can show that each magnon branch, in this case, has a chirality. Each magnon branch carries a spin, actually. And the spin carried by, so if you would now actually have send a heat current from along this y-axis, you will affect the one type of chirality, one type of spins, one type of magnon bands differently, so when you send heat in this direction. So also in this paper, we showed that a heat current, in this case, carries a spin, which is the equivalent for, in these insulators, of the band in the electronic system where the electrons carry a spin. Not only that, we have these 2 different branches, but we can also ask ourselves, what happens if we break the symmetry, slightly break this altermagnetic symmetry? So we perform some strain. So in our minds, we pull the system apart in one direction, which means that the Jx is slightly different from the Jy. The interactions along this diagonal become slightly different from the interactions along that diagonal. And you can ask, okay, now I break the altermagnetism, do I get a ferromagnet out of it? And that's a kind of general theme, I would say, in this field, that you can say, well, you know, I have these well-known ferromagnets. I have these well-known antiferromagnets. Where are the altermagnets? They're somewhere in between, somehow. Because I need to break only one symmetry, this rotation symmetry, to make them out of the class of antiferromagnets. I break one symmetry, and I am dealing with something that actually is a ferromagnet. So an altermagnet is a very susceptible system. Breaking of rotation is kind of easy. Such a strain does exactly that. And if you break that rotation, you get out of the altermagnetic paradigm. You get out of this altermagnetic symmetry that forces the two sublattices to be compensated, to have zero total magnetization. So if you break that symmetry, in general, you will get, well, symmetry allows, you get a ferromagnetic moment growing in your system. And this is what we showed in this paper, just to give you a flavor. This is temperature, and this is the magnetization, or related to the magnetization that you have in the system if you squeeze it a little bit, if you strain it a little bit. And you see that at zero temperature, in this case, in zero temperature, there's no ferromagnetic moment arising. But if the temperature goes up and the fluctuations become stronger, the system starts fluctuating, now I get a total ferromagnetic moment in this system. So I started with an altermagnet, I strain it a little bit, I put on temperature, and I get a ferromagnetic order out of it. Okay. Another, so that's the last one I'll indicate only. We did a lot of work, it's a talk in itself. It's about the Hall and anomalous Hall effect. So just to remind you, Hall effect is I have an electrical field and a magnetic field, and I look at the current. I look at the current that's orthogonal to both electric and magnetic field that are orthogonal to each other. So I have my hand, I take my right hand, and I know that, you know, I have, for instance, here electrical field, magnetic field, and I know where the current is according to the right-hand rule. Yeah? So an external magnetic field defines the direction. And this is, of course, the Hall effect known since 1879. And the anomalous Hall effect is the same thing. I have a magnetization that tells me that when I have a current applied, in which direction the current perpendicular goes, right? So I always need I need three vectors. I need, for instance, the magnetization. I need the applied electrical field, and I know that my current is in this direction. Now you would say, okay, that's all symmetry allowed and kind of obvious, but you can ask, can a Hall effect occur in zero external field and in a system with zero magnetization? So you say, okay, there now I have to think, because yeah, I can apply an electrical field, but now I don't know where the current is going because I don't have the vector of the magnetic field or of the magnetization that gives me the right-hand rule or the left-hand rule. I don't have a vector to work with. And this is now comes from symmetry. From a symmetry analysis, you can say it's known, it was known before, that yes, you can have an anomalous Hall effect because only time reversal symmetry breaking is formally required to have an anomalous Hall response. However, if you have a symmetry that's time reversal times translation, you kill the anomalous Hall effect. So this is all antiferromagnets that I talked about before. All canonical antiferromagnets have this symmetry, so they cannot have an anomalous Hall effect. However, it's exactly the altermagnets that do not have this symmetry. It also involves a rotation. So the question, in principle, altermagnets may have an anomalous Hall effect. by symmetry. And we asked ourselves, that sounds kind of crazy and strange and interesting. Can we make a small model where that you can explicitly show that this happens, right? Because one thing is saying symmetry allows, and the other thing is here I have a model where it happens. And we did, and like I said, it's one talk in itself, but I'll just tell you that we observed the anomalous, altermagnetic anomalous Hall effect in a Kane-Meili model, which is a two-dimensional model. If you add electronic correlations, and the point there is, what you learn after doing the work is that there is a sublattice magnetization. That is the difference of the magnetization on sublattice A minus B that also defines a direction. So there's a Néel vector that defines the direction. I have sublattice A and sublattice B. A minus B is this. This is a direction. B minus A is this direction. So in this altermagnet, this Néel vector sets a direction, which means that the anomalous Hall response for an altermagnet that has this Néel vector is opposite to the one that has this Néel vector. So this flips the anomalous Hall response. Okay, so conclusions. There are really a bunch of altermagnetic materials. There are more than the 60 that we came up with in the meantime. I'm sure people are looking for new materials that also will fit the bill. The metallic ones, metallic altermagnets are scarce, but I think they're interesting. Ionic altermagnets tend to have large spin splittings. And I would say that altermagnets are predicted to have interesting properties. And this list is by no means complete. Spin transport is interesting, like I said, or tried to convey. Spin heat transport, piezomagnetism, anomalous Hall conductivity. I talked about that. Our paper of Friday was about wild metallicity. So there's also topology. Topological effects and topological edge states in chromium and timonide. You can ask how the magnetic domain structures are different. And indeed, magnetic domain walls carry magnetization. We have shown that with the Mainz group together. You can ask what happens if you make two-dimensional curved nanomembranes. You can ask about optical and magneto-optical properties. And I think they all show, at least in theory and at least in symmetry, interesting new effects. That was it. Thank you for your attention.
Thank you very much for this very interesting and educative talk. Are there any questions to the lecture?
Thanks, beautiful introduction. Although you didn't beat Libor, because Libor was speaking about altermagnetism, and the background was dancer in the black and white, depending on the spin direction. And he was describing altermagnetism using this dancer. So still a way to go. But I have some questions concerning the last slide you have shown. Is spin-orbit interaction included in this? Because the question is, do we need spin-orbit interaction for anomalous Hall effect?
Yes. Yeah.
So this brings me, what I suspected, this brings me to another suggestion that maybe this vector you look for, it could be, of course, the same direction. In some cases, in some cases not. It could be orbital magnetization direction. What do you think about? Could you comment on that?
Yeah. So your as to your first comment. So if you talk about the Hall effect or anomalous Hall effect, there needs to be something that couples to the lattice, that you need spin orbit coupling one way or the other, and this is maybe also to stress this. So and people. Paul McClarty, for instance, that did a very nice Landau theory of altermagnets, stresses this all the time. that the altermagnetic symmetries are symmetries of a system without spin-orbit coupling. That is completely well-defined, of course, theoretically. Does any of such a system exist in real life? No, because there is spin-orbit coupling. So any spin-orbit coupling will always tweak or bring you out of this purely altermagnetic, fantastic property, and then you have to ask spin-orbit coupling, small spin-orbit coupling, with respect to the exchange splitting, what does it do? For the anomalous Hall conductivity, you need the spin-orbit coupling in the end. But still, you would say that this large energy scale of the altermagnetism is kind of setting the stage for it. The finite spin-orbit coupling also means the finite orbital magnetization. So that's another way of looking at the same at the same physics and say, okay, actually, it is an anomalous Hall effect caused by an orbital magnetization. I'm also fine with that. I wouldn't want to split hairs on it. So personally, I would say when I was confronted by altermagnetism and said, okay, people said by symmetry you're allowed to have this anomalous Hall effect without any magnetization, I told my students, this is wrong, let's prove it's wrong. And it turns out to be right. So that is, conceptually, I find interesting. Yeah.
Are there any other questions?
Thanks a lot. So just two questions. So the first one is with the checkerboard model. So would you think it's like can it be considered as the minimal model for an altermagnet? Yeah. Is it a minimal model for an altermagnet, this checkerboard model?
I would say it's a minimal model. All right, it's minimal enough for me to understand it.
Yeah. But can you think of something even simpler, or rather?
You can think about something simpler by just putting, let's say, core spins on a lattice, or having spin splittings that you define. You can take your band structure and just fix the hoppings for one spin species and the hoppings for the other spin species,
yeah,
and then you get an altermagnet, even simpler. But that, I would say, it doesn't show any collective effect, right? Yeah. So if you want a transition in the same model, a transition from something that's not altermagnetic or paramagnetic to something that's altermagnetic, then you need something at least Heisenberg-like, and that's the checkerboard, I would say.
Okay. So if I may, a second question. So you mentioned that basically most of the altermagnets so far are the localized systems, yeah, if I understood correctly, yeah? And there are not so many itinerant ones.
Correct.
So what's the reason? Is it this spin-orbit coupling, something more? Or what's?
Yeah. So that's a good question, and I do not have a definite answer. I can only make the observation, how many metallic antiferromagnets do we have? And there are also not so many, right? Yeah. So metallicity and antiferromagnetism are not natural partners. And that's kind of, we understand this, right? Because of double exchange and kind of things.
Exactly. Yeah.
So that's why metallic antiferromagnets are not so common, and therefore metallic altermagnets are even less common.
Thanks.
I should also say about spin-orbit coupling, now we're just saying it. So the localized antiferromagnets, altermagnets, what will spin-orbit coupling do to them? And you can show that all of these systems have the symmetry that DMI is allowed. So you will get counted, in general, you might get counting of spins, and you will get a small ferromagnetic, weak ferromagnetic moment because of that. So again, they're going beyond purely the altermagnetic world, including also spin-orbit coupling, will give you a symmetry breaking and can give you in general ferromagnetism. It must not, but it can.
Thank you for your talk. It's maybe a follow-up question, and it's great to have you here because we also here grow and study altermagnets a bit. My question is about, yeah. Could you elaborate maybe on possible applications of this insulating or wide gap altermagnets? Because from my understanding, the large interest initially came due to possible spin currents or anomalous Hall effect, but would you like to say a bit more about this insulating altermagnets applications?
Okay, so you're asking theorists about applications, right? So so you get a theorist answer for that, and I'm not sure if you will it will help you. But I would really, I mean, as a field, I would say let's all these applications maybe we'll get there. Let's first we have some concepts. Let's prove that those concepts are really measurable in materials. What I would really like to see is one of the concepts that you have is that magnons carry spin in this case. Magnons carry spin means heat currents carrying spin. Can you show that there's indeed this happening and that the spin carried in different directions is opposite to each other? That's a simple prediction. Then we have shown work on domain walls, that the speed of domain walls in altermagnets is different. You can ask things about scattering of electrons at domain walls. So in general, let's say an altermagnetic domain wall, so in this localized systems, so you have your spin or your nil vector doing a rotation like this. So you do a rotation like this, and you can show that there's a magnetization associated to the domain wall. So here's the magnetization positive, then you go through zero, and the magnetization is negative. So if you find a domain wall in your localized altermagnet, my prediction is look at the magnetization, there should be a magnetization changing sign across the domain wall. Another prediction is that chromium and timonite, this is not published yet, domain wall in chromium and timonite. Now I have a metallic system that is an altermagnet and a domain wall. There is, because of the symmetry of chromium and timonite, no anomalous Hall conductivity associated to it because the spin is pointing in some direction. We have shown that if you have a domain wall, there is an anomalous Hall conductivity associated to it. The anomalous Hall conductivity from a domain wall in an altermagnet, where the nil vector goes like this or the nil vector goes like this, is opposite. So this stuff is just stuff I know because it comes from my group. There are many more predictions out there. I would really say let's try to find this, and then thinking about how if altermagnetic domain walls are maybe better, altermagnetic skirmions are better than antiferromagnetic skirmions. That's a question that will need some time.
So thank you for your talk, and I have a question about extending this altermagnetic phase to non-collinear systems. Does such thing happen?
Sorry,
Non-collinear systems, because you have, like you said that this group theory considerations that they apply to collinear systems. What about the non-collinear ones? Do you have like a similar idea, and you can extend it to those systems?
So the Minds group has been working on that in part, also non-collinear systems. My personal flying route is a bit different there. So it's known that in non-collinear compensated systems, you can have spin split bands. I mean, this is really well known. So the spin splitting in non-collinear antiferromagnets, I'm not so thrilled, or it's not so cool, let's say. But what is cool is actually, and it comes from the symmetry analysis of McClarty. So if you do Landau theory, a way to understand most of this from that perspective is that I have a primary order parameter, an antiferromagnetic order parameter, the nail order parameter. This guy sets in below some temperature. What happens in an altermagnet is that I couple linearly to another order parameter. So I have a linear coupling to something else. The nail vector couples linearly to something else. Yeah. And this, for instance, can cause the anomalous hole conductivity. Yeah. This, in this model that we have, it opens up some gaps in the system. So the linear coupling of the nail order parameter to another magnetic order parameter gives you all kinds of new effects. It really means that at the phase transition, there's a secondary phase setting in, and the secondary phase is giving rise to all these altermagnetic properties. And that actually translates one-to-one to non-collinear systems. Yeah? So you can, a way to understand this spin polarized currents is exactly the same way. You take a system that has a nail ordering and you look if it has this altermagnetic symmetries, if you can get spin currents that are directional dependent. And the answer is yes. And if you would do it for a normal antiferromagnet, the answer is no. So now you can say, well, let's do a non-collinear antiferromagnet. Is the answer yes or no? Don't know yet. So I think that is more the flying route that I would take in that case.
Maybe the last question, or maybe two last questions.
Very nice talk. I would like to come to the beginning and not talk about this all transport stuff and all of this, but go to the lowest energies actually, because you have pointed that we have like ferromagnets, we have like zero magnetic moment, which is antiferromagnets, and the class like we can think. I think we can think of a class of antiferromagnets as these altermagnets. However, I would like to also say that we have also frustrated magnetism, and to me, because I'm researching frustrated magnetism, this is like it can host in the ground state very highly entangled states, like dimer states, and what I'm interested in, if we can also find, looking for like we can also find like some topologically protected states in the ground states of these altermagnets. However, I would also like to point out that I have not found, I have only found one article, one archive article that have used some tensor network methods for only for magnons and not for the ground state. Is it too hard to do? Do you know something more about some progress in this area in the context of, for example, DMRG? I would last thing. A month ago, there was also another guy from Pan from Magtop, and he said that we cannot have one-dimensional models because not all of the effects are like can be taken in one dimension. We need to have at least 2 dimensions. And I think it may be possible to maybe study, but nobody has yet studied it, I think, with maybe some higher dimensional tensor network methods than some DMRG, for example, some PEPs, for example.
Okay.
Yeah, that's all.
So thank you. So if you want to study frustrated altermagnets, I would strongly encourage you. I think it's I'm sure people thinking about it, but there's no work, almost no work published. You need to go to 2 dimensions, at least 2 dimensions. And one of the questions I would ask my students is, so now I have a system that has magnetic frustration, if you're interested in frustration, which means that my ordering that I would normally expect, the antiferromagnetism, is likely not there. So can I now have an emergent altermagnetic order parameter? So now I have a system that has, no predefined. My checkerboard lattice has already put in hardwired the altermagnetic symmetries, right? So now take a system that has no hardwired altermagnetic symmetries, that's very symmetric. Can it spontaneously form an altermagnetic order parameter? And why would this altermagnetic order parameter be better than an antiferromagnetic order parameter, for instance? I mean, those are things that are, if somebody would give a talk, I would go there and listen to hear what they have to say.
So that was the last question of today's colloquium. I invite you for 10th of June. It will be the last colloquium in this semester. So thank you all for coming, and have a good afternoon, and let's talk our speaker once again. Thank you very much.
Thank you.